Bill,
Good morning.
good morning. How are you?
Good.
That's good.
Yeah.
I guess Jesus will be coming on in a minute.
Yes, I haven't seen him yet. I presume that he will arrive soon.
How's the weather? Do you have snow like in New York?
Pretty much the same. There is some snow. It's warmer than you might expect at this time of year, but nothing dramatic.
You know, Buffalo had 6 feet of snow.
Yes, yeah, that's famous already this year.
Yeah, that's
But no,
something.
we didn't see anything like that.
We had a couple of inches last year, but this year I don't know what we're going to get anything down here.
You usually end up with rain, I suppose. I've seen the weather report saying there's a system moving out of the Gulf that keeps crossing over northern Florida and Georgia and so forth. But maybe it doesn't get as far north as you are. I'm not sure.
I like to have a little snow. I really enjoyed it last year when a couple of inches, 2 or 3 inches fell.
That's all you need. Yeah.
Yeah, it only
More
lasted
than that,
3 days, then it was gone. Well, I've been
I'm
working hard this week still. How about you guys? How about you?
sorry, your audio is breaking up a little bit.
I was saying I've been working pretty hard this week on these ideas. How about, have you thought about it anymore?
Well, I read through your the null vectors paper that you referred to. You said you were going to discuss it uh, with your local math department. Um, I I didn't find a, a lot of points to think about in it. I guess maybe for me the difficulty is the physical applications aren't so apparent. I mean, it's clear that you're establishing or elaborating on this connection between graph theory and Clifford algebra.
Yeah, that's interesting. That Russian woman actually has a paper on Clifford algebras and graph theory, which I found very
Yes,
late actually.
I saw that reference in your reference list of references, and so I did take a quick look at it. That paper, seemed pretty straightforward. What you're doing clearly is an elaboration on that same general idea,
The same idea.
significant elaboration, right?
Yeah, yeah. Actually, I did talk to the department chair at Clemson University, and well, I'm not sure whether they're going to invite me to give a talk about it or not. But
Well, yeah.
I'll be going to Mexico on December 6th. So if I to talk about it before then, it'll have to be the first week of December. But they might not invite me, so it's fine. But I do have some new ideas to clarify it. But I'd like to let it'd be interesting to see if Jesus has something to say about it as well. And then,
Yeah.
and
So
I'll
at this
share
point,
with.
I'd say I don't have a lot of comments. I have a couple of, well, just so far, just one sort of uh, just a moment of uncertainty at the end of your paper where you're giving that conjecture on the number of Platonic solids. Um, so maybe it's a typo in the paper or something. I'm not sure. So I can bring that up.
Well, yeah, that's good. Let me just say, I see Jesus has come on too. That's good. But I'd like
Good
to. Good morning, Jesus.
Good morning. Sorry for this delay. Sorry.
Oh, that's
No
fine.
problem. I should mention also at this point that I have to leave our meeting a little bit early. I need to leave at about 10 minutes after 12. So in about 1 hour from now. But of course, if you're in the middle of discussions, you know, I'd encourage you to continue, and then I'll catch up.
Well, you are in control of the session, I believe, right? You're the master.
No, well, but it doesn't require that I be online. I
Okay.
ensured that again. Initially, that was a problem, but I've changed the options on Zoom so that the meeting would continue even without the person who initiated it.
Yeah, I might just also mention I did share the same paper with Dr. Havel, Timothy Havel. Did you remember Timothy from before? I think you met him. Maybe not. Did you ever meet Timothy Havel? Tim Havel?
The name not familiar to me.
Okay, well, anyway, he had also some credit. Well, I can see why. The paper really was just not even well, it's a preprint now, but I'm not publishing it as it stands because my knowledge of graph theory is not adequate to be represented. And, you know, I made a lot of mistakes. So, but anyway, this new thing I've got, which I'll talk about after, we'll see what Dr. Cruz has to say about, and then maybe I'll have a little time well, whatever you guys want to share, and then I'll show you what my new ideas are, which I think will clarify everything.
That's always good. So just before you arrived, Jesus, I admitted that I didn't have a lot of comments about the paper as it stands, but I'm looking forward to seeing more applications. You know, since the paper as it stands looks quite mathematics, like pure mathematics. But the proposal, at least the outline of the paper, Dr. Sobczyk suggests a large number of potential applications going beyond just its connection with graph theory. So that's where my main interest would be focused. Plus, I did have one comment about the last conjecture on the paper. So at some point we can get into that. So that I just mentioned that just before you arrived, Jesus. So maybe you could say something about it.
Yes, I was working with Professor Siewicz in the subject of graph theory and graph of multigraph. And then we published 2 papers in this subject. And after the presentation last 2 weeks, this section before, I thought about taking some ideas from there and then incorporate to this to this discussion that we are started. And I was working with some of the package of Mathematica for getting some graphical presentation of this, but and I have some, but I think that the most important point is how we can first extend the idea of graphics and then take this idea of graphics and apply to different kind of problems. The first one was the Clifford algebra. In general, we can present some kind of graphics to algebras in general. But if we want to work with Clifford algebra or Grafsman algebra, we can we need to find more specific properties in these graphics. Then I think that this is a good way for working in this subject.
Okay, I find that very interesting. If you have anything you'd like to share screen with, that we could look at that, and then I can talk about what I've found. I'm pretty excited what I found out, actually. So, but
okay, well,
go ahead if you'd like to present something first.
Sure. Let me just ask my technical question about your conjecture at the end. So I'll just reorganize my screen here a little.
Let me just say about that, this Dr. Havel, he's actually associated with MIT, has written a paper called Hadron's, is it Hadron theorem? Hadron's theorem extended to the tetrahedron. I think that this is, I actually referenced his paper because I believe, what is that Greek, is it Hebron or what is that Greek? Heron, I think it's Heron's theorem to the triangle, extending that some result that he has to the tetrahedron, and he was very excited about that. And I think that's very closely related to solid platonic solid can be attacked by the approach that I'm suggesting. But so that first paper is, like I say, is really a preprint, and very many errors I made regarding graph theory, which I think I can avoid right now.
Yeah, well, certainly for a wider audience with people who are much more familiar in depth with the graph theory terminology, that's quite critical.
Yeah, I might mention that at Clemson University, the chairman recommended I talk to a graph theory expert at Clemson University. Well, I gave him a copy of that same paper, which Jesus has now put on the screen. And I said, please share it with him and see what he has to say. And then that was the long and short of my thing with Clemson University. But it's very interesting.
Yeah. Well, you mentioned in your email, I think that graph theory is an enormous subject with a very long history. So
I'm ignorant basically in it.
Yeah. So so it's difficult to make claims in graph theory without
knowing what you're talking about.
A lot of preparation, but it is very fundamental, and so it's quite important. One comment I was going to make, which comes to mind right now, is that in some sense, graph theory is a foundation for category theory.
Yes.
Okay.
Especially when you consider directed graphs,
Okay.
since the edges of a directed graph can be associated with morphisms in a category. But of course, the category adds more structure to that. It adds the notion of composition, but that corresponds just to paths, directed paths in the graph. So there's that connection, and because of that connection, I should mention in category theory, one of the most fundamental symmetries is duality related to the direction of the arrows. So if you have a category in which the morphisms are directed one way. If you flip all of those morphisms around and they're all directed in the opposite direction, then that category that has those morphisms has very specific properties in relationship to the other, right? So this is like called generally referred to as a categorical dual. And so in the work that you're doing, Dr. Sobczyk, I think there is the possibility to study that kind of duality because you're dealing with directed graphs as sort of underlying the signature of the
Okay, very interesting.
So the reason why I thought about that was I checked your paper quickly for the use of the word duality, and it only occurs once in a credit that you have referring to work with Dr. Oshevich. But in the end, I didn't find much else in your paper about duality as such.
Well, now I talk in terms of correlated null vectors, but maybe Dr. Cruz has something more to say.
Well, sorry, I am trying to connect my other computer because the mathematical calculation and those are in this computer. Then I am need finish.
Okay,
that.
well let me just ask my one technical question at the end. So I'll just skip to the end. And
oh, okay, so you're Dr. Page is sharing the screen then right now, not Jesus. I thought Dr. Cruz was
yes,
sharing it.
No,
Okay.
no, this is I just brought this up because I marked this at the end of your paper, and I was wondering, I didn't understand quite what this is. So
Okay, well, I'm trying to relate the idea that I was talking about to this very important result regarding Platonic solids in 3 dimensions as well as in any number of dimensions, and of course the references to this John what's his name? Results of
so my first just
John Baez, of course, I give him credit for that's where I found this result. I think that it can be proved very nicely using this formalism. I'll say a little more about that maybe later on today if we have time still.
Yeah, because maybe, well, my first confusion just was to distinguish typographically between this sequence and I guess these are references, like these are.
Yeah, that goes to the end of the paper. That's right.
Yeah, so I was sort of wondering, I didn't understand really just typographically what you intended here. So,
that's the reference. Yeah.
Oh,
Sorry.
little extra feedback there, right?
That's right.
Yes, sorry.
Yeah, so if I were to take a look at Baez here,
that's a beautiful reference, by the way.
That's reference 4. Then I would actually see this conjecture worked out in some detail. Is that?
Not really, but he discusses the Platonic solids and extends it to infinite dimensions. But very nice graphics, it's beautiful pictures of the Platonic solids. And then this result that they know is well-known result, I suppose. It's not well known to me, but I was fascinated by it in relationship to what I'm trying to do with what I call projective graph geometry.
Yeah, well, I guess I just got confused at this point because I didn't seem that the conjecture was obvious to me, like given what you had.
No, it's not obvious.
And I didn't. It sort of came out of the blue, and I sort of wasn't seemed a little disconnected in terms
Oh,
of
well,
the development in the paper.
it's just a conjecture. Well, I say it's obvious, but it's not obvious, really. But it is true. Well, the result is true because of what this John Baez's reference number 4. So you can look at that when you have time sometime.
And he refers to the Laplacian in the same.
No, he doesn't. That's the tools I think I'm developing that which can be used to get that result.
So you don't actually calculate that here, right?
No, I don't. I don't calculate anything there. I do calculate the Laplacian of x and Laplacian squared, or well, the gradient of x at the top there of the paper, and the gradient squared. I first define what those operators are, and I try to calculate it for the simplest case of position vector x and the position vector x squared with the Laplacian, which is an interesting result, which I'll, if I have time, I will show you some new ideas and fit it together a little bit better.
So I guess I just don't quite understand what you mean by the zeros of this equation.
Okay, well, maybe it's not even correct, so I don't want to say anything more about that at this point, but keep that in mind, and I'd like to talk about that some other time maybe, but.
Okay. So that's my comments. Jesus?
Okay, thanks. Sorry, I don't put too much attention to your comments, but I am to review later those. Okay, first I am going to present to you some basic ideas about graphics. I'm going to share my screen for that. Okay, it's better. Yes. Okay.
Okay.
Maybe. Okay, I think you can see this now. I am using only some built functions in Mathematica for doing that. This function is graph, and then one only needs to put here the edges that are connected for present this graph. Here we have one non-directed graph first. Then this is the kind of connection between not connected vertices. Okay, it is easy to show a graph here. Only putting names in the vertices and including here or putting like input the connected vertices, and one can change the kind of connection. For example, I hope to remember that is no. I wanted to change this kind of direct is okay. No, I have one directed edge here, and the other one are not directed edge. Then it is easy to show different kinds of graphics, only adding the corresponding edges in the required quality. But there are another functions that I think that it is the functions that Professor Garret like that we work, because those are complete graphs. Then a complete graph have in general direct edges, and then again I have get different kinds of complete graph, only changing the order here. Then instead of yes.
One comment is that the definition or implicit definition of complete graph in Dr. Sobczyk's paper is slightly different than what you're showing here, right? So this
Mine might well be wrong.
well, it's a matter of definition, as long as you're clear up front, which you are, you know. So
okay, no, maybe I'm all right.
So
maybe it's not this different. Maybe it's the same.
Well,
actually,
the terminology that is being used here for complete means that there are directed edges in both directions between each node.
okay.
Whereas in your case, you considered a graph complete, a directed graph complete, if there was any connection, either left or right.
Yeah, that's true. Yeah, but yeah.
So your concept of complete is more like completeness in an undirected graph, but then assigning a direction after the fact. You know?
Yeah, I think that's correct. That's why I say we're getting into the terminology of graph theory, which I'm really not all that familiar with.
Yeah, so I don't know exactly the terminology, the standard terminology in graph theory for the kind of complete directed graph that you define. So as long as you define it clearly as being that's what you mean,
okay.
I don't think that's a problem, right? It's just.
But I think that the standard terminology in complete graph is that all the vertices are connected and those are connected in twice directions, in the two directions. But I think that it is useful for the idea. Because the direction is connected after with the weight of the connection. Then for some kind of connections, we can use one weight, and in the contrary sense, we use another weight.
Yeah, maybe the weight could represent the distance between the vertices, at least in the case of the picture you have there. Of course, in higher dimensions, then it would be the surface area between faces of the graph, than in the higher dimensional case.
Well, in higher dimensions is the sense of an N graph, right? Like a two graph has edges that are surfaces, right? A three graph has edges that are volumes, right?
Exactly. In higher dimensions.
That's the notion that Jesus and Oshevich were presenting in their.
Okay, well, that's extremely interesting, because what I have now, well, I'll share it with you. I hope before Dr. Page leaves, but maybe leave me 10 minutes will be all I need to, well, I'll share screen then as well. I'd
Sure.
like to show both of you what I have, but I like, go ahead with Dr. Cruz's very nice pictures here that he's sharing with us.
Yeah, okay, but if you like to present now, maybe I can interrupt and after I can continue with
Well, no, I think, well, let's take, if you have like maybe 10 minutes to finish, I think, you know, that would be okay.
Okay. Then, okay, this is only different kinds of useful functions here in Mathematica that we can use for this purpose. And then after, okay, I'm going to pass this and here go back to the
very beautiful graphs, very beautiful.
yes. Okay, we have here again the fourth vertices graph, and now I like to put one weight in the graph, and then this have not a difference in presentation, but we can get the weighted adjacent matrix that how you can see here are weighted in the way that we want. Here is not the weight that Professor Garret Sobczyk is using. This is only one example of how we can put here the weight.
That's adjacent matrices that you're talking about.
Yes, I am talking
Directed, I guess.
about the adjacent matrix that have the weighted of edge of the graph. This is the idea. And okay, but here I go to the with the weighted that you were using, and now the adjacent matrix for the weight is this. I think it is too much useful because this can help to us to get different paths in these graphics. Then I am go ahead and get different kind of paths paths in these graphics, but those okay, first is only one example of the paths, but after I am going to get only the paths that are starting in the node 1 and end in the node 1. That I think that was the idea of this. Okay, and then I'm going to start here again. I define these graphics here like CG3, and after I am going to work with this, I get the list of edge, and then I highlight the first cycle here. Then, sorry?
Beautiful, very beautiful.
Okay, I have another one, a cycle here. And after a third cycle. I don't know if you catch the red color here.
Oh, yes.
Oh, okay, okay. Then we can find the different kind of cycles that we have. Maybe only for remark, you can see that we have here a first cycle going from vertex 1 to vertex 2, vertex 3, and then again vertex 1. This is the idea. But now we have here a different path. No, it's repeated here. Now we have here a different path that is going from node 1 to node 2, then node 3, go back to node 2, and then node 1. This is the second, and then we can have one more here. There's one problem here, is one that is needed. Sorry, here is the first, from node 1 to node 2, and then again node 1. You can see the complexity in the path. Then first, we only need 2 edges for this path. The second needs 3 edges for going in that path. And then after the third needs 4 edges for get that path.
Jesus, just one comment is that the display of the graph is somewhat ambiguous, right? Because you could get that same highlighting with a different path.
Yes, I am highlighting in the graph C G3 different paths.
But you could have another path that is a slightly different order, which displays the same highlighting. That was just a small comment.
I don't see that the another path for another set of edges.
For example, to go from 1 to 2, and then back to 1, and then to 2 again, and then to 3.
Yes. But the condition here is that I cannot use 2 edges in the construction of the path. Building the path, only I can pass 1 time in each edge.
Okay.
Yes. Sorry, I just don't clarify that. Here we have now the paths that are from 1 to node 3 first, and then from node 3 to node 1. And again, we have these 3 different kinds of paths that we can build. Okay, and this is the principal idea here. We can show how are building them, but now I wanted to review the building of graph from the theory of graph. And then I'm going to the sorry, I lost here. No, I lost the articles that I was select, but I have here.
Could you send a PDF file of those pictures that you showed? Is that possible or not?
Not yet, but I can generate some a PDF and then I can send to you.
I'm very interested to see if we could apply this theory that I'm trying to develop to exactly the types of things you're presenting, which is very interesting to me. And if I have a few minutes, I'll present you what new material I have then.
Okay, I send to you.
Yeah, send me that paper as well. Please send me that one as well.
Okay, and then here I have this paper that was published in 2003, and then I'm going directly to the pictures that I think that are the important point here. Here there is one different way of presenting the graph, no? That are relating two kinds of objects that are the edges and the vertex. And then we need two functions or morphisms that are source and target. This is the way that we can build a direct graph. Then with this, we can have different kinds of direct graph, but even we need to associate with different kind of vertices and edges this couple of morphisms. Then with this is a very important idea here in this paper, because with this relation we can go to to build more complex graph objects. Then we are going to use this terminology associating edges and vertices with cells. Then we have 0 cells, 1 cells, and so on. Then with this idea, then we can extend the concept of graphics to more complex graphics that I have here different kind of graphics, but those are not important in this at this point. But then we with this idea we can go to the idea of multigraph that are graphics of higher order. Then with this we build in the same way, connecting elements of G1 to elements of a higher order graphics. Then we need to connect the one graph with two graphics. And this permits to us to build two most complex graphics. One general idea of this is that we can build hierarchical systems in terms of graph, and then analyze these hierarchical systems in this way. Okay, here is a more generalized definition of N-graph, and here we have this sequence of graph that we can build. Here in the graphics, we are thinking in reflexive graphs. Then this adds to the two functions, and this function that is the reflexive relation. Okay, then with this, the idea is that maybe I can stop sharing here, because this was not possible to okay. Possible
Okay,
to,
so please send me that paper and also a PDF of those figures earlier. I think that would be great if we could apply the theory which I'd like to present. I'll just read the abstract. Well, I'll share the screen with you and show you the abstract of what the paper is, and later I'll send you a copy of it, of this newest ideas that I have, which I think develop a powerful analytical tool in which to study the graphs exactly what you're talking about, which I think would be great if we could combine these ideas together.
Is this an extension of the previous paper or a new paper altogether?
Well, no, it's an extension of the previous paper. If you want, I'll share my screen and try to get it up for you to see it at least.
Yep.
Okay, I'm going to share screen now. I can get in here. Okay, can you see that?
yes.
Yes.
All right, let's see if I can move down here a little bit. Oops. Okay, is everything all right? Can you see it? Okay, so what I like to just mention is that in trying to further this theory that I'm trying to develop, which I think is new as far as I know. Okay, so I call it light cone projective graph geometry. I'm going to show you the Cayley-Grossman theorem. Well, that should strike for the Cayley-Hamilton theorem. I believe what I'm going to show you now is extending the so-called Cayley-Hamilton theorem, or another way of looking at it, where a more appropriate name would be the Cayley-Grossman theorem. So I'm trying to develop analytic tools to study exactly those detailed graphs that Jesus has presented now. So let me just go down a little bit and read this abstract to you. Okay, a sign graph is a graph in which every pair of vertices is connected by a directed edge. By geometric, okay, so this is, I've talked about before, a null vector V is an algebraic quantity with property B squared equal to 0. I denote the universal algebra generated by taking all sums of products. Okay, that's from before. The rules of addition and multiplication and in taken as familiar rules of addition, multiply real and complex square matrices. I define a pair of real null vectors to be positively or negatively correlated if their inner product is positive or negative respectively. I began the study of linear algebra in Rn in terms of signed n-1 simplices whose vertices are named by non-zero null vectors. So this is, I think, a new idea, which is the basis for this new light cone projective graph geometry I am abbreviating with the symbols LPGG. Okay, any theorem in linear algebra can be studied in terms of light cone projective graph geometry on a signed n-1 simplex, which I denote by S plus n-1 contained in Rn, using the powerful tools of projective geometry in a suitable geometric algebra. Gives a reference to. I give a new proof of the Cayley-Grossman theorem, which is really no more than an identity in this newly minted geometry. These ideas provide the foundation for a new Cayley-Grossman linear algebra in LPGG. Okay. So there I'm just defining more specifically these different ideas here. And I'll just go through this quickly. But I won't try to talk any details, but I'll just show you. And then I'm doing actual calculations here. Important geometric algebra, GA identities. Okay, I'm just giving identities now, calculations, which I think we can apply to graph theory, defined by, in this case, well, I'm doing it in the simplest case of S1 plus, as you see in equation 4, okay, S1 plus by 2 vertices. Unfortunately, I don't have any figures yet, but I need to develop simple figures to go along with this. Okay, so this relationship you see, number 5, is very interesting. Okay, expressing the position vector x in R2, any position vector in R2, uniquely in terms of its LPGG projective coordinates. Okay, you can see any 3 vector dimensions, any 3 vector in 2 dimensions is 0 automatically. And if you just expand this, you get this expression, x minus this projection expression, note involving only the outer product times V1, that's the vertices, and V2 is the second vertex, equal to 0. So you can see x is equal to, you just put on the other side of the equation, expressing the position vector x in R2 uniquely in terms of its LPGG projective coordinates. Of course, the trivector V1 wedge V2 wedge x is equal to 0 because we are in R2. Okay, so remember, V1 and V2 are the vertices of a 1 simplex, which I call S1, directed 1 simplex. So I'm taking the direction V1 to V2. That's understood. But of course, we could turn it around and make it minus if we want, but I'm only studying positive correlations now. Okay. Okay, and multiplying equation 5 by 4 times V1 wedge V2 squared immediately gives what I call the Cayley-Grossman identity, which I've called in the beginning of the title, the Cayley-Grossman theorem, but it's really an identity. And here it is. Given any linear LPGG linear endomorphism in R2, we have this identity. Instead of the characteristic equation in R2, for usual characteristic polynomial, we have a function satisfies its characteristic polynomial. So this is f squared x minus 2 f of x dot v1 times v2 plus 2 this f dot v1 reverse the thing equal to 0. So that's what I'm calling the Cayley-Grossman identity. Okay. Okay, now I'm solving this equation. The interesting thing is the eigenvalues of this any linear transformation that I'm studying in LPGG endomorphism and geometry, the geometry is plus or minus the determinant of the coordinates of the vertices, V11. So the vertex V1 is equal to B11A1 plus B12A2, and so on, okay? So the eigenvalues are f of A1 equal to V1 wedge V2 times A1 is equal to the determinant of this the two edges, well, the directed vertices from for the vertex V1 to the vertex V2, the coordinates are V11, A1 plus V12, A2. Okay, so the determinant of the coordinates gives you the eigenvalue. The eigenvalues of these linear transformations in LPGG geometry are just the null vectors A1 and A2. Okay, so you have to look at it a little more detail. Okay, now I say matrix formulation. So I can translate any equation now in LPGG geometry into a matrix formalism. And that's what I'm doing here. So here's our general linear mapping in LPGG geometry. Okay, so that's a mapping. F of x is equal to 2 times V1 wedge V2. That's the defined on the remember V1 and V2 are the names of the null vectors naming the points in our one simplex. Okay, so the matrix of this mapping, this is the unusual thing about this, is equal to 2 times the V1 wedge V2 times X. That's the same thing as 2 times the matrix of the bivector V1 V2 defined by these nilpotent vertices times the matrix of X. Now let me go down, you can see what that is. Okay, so here I'm working on what the matrix of V1 and V2 is. Okay, and I get the, okay, so the matrix of A1, well, that's what we talked about before, is a 0, 0, 1, 0. A2 is 0, 0. So when I talked about before, A2 is B now. So it's completely compatible with everything I've said before, and which is defined in the book that my book, Matrix Gateway to Geometric Algebra, Spinners, Space-Time and Spinners. Okay, so there's the matrix of X. The position vector X in this LPGG geometry is very strange. It's actually a 2x2 matrix, okay? And here's the matrix I found for the bivector connecting the 2 points, V1 on the simplex, it's a one simplex, which defined by 2 vertices, V1 and V2. And this is what is, okay, notice that this thing here is just minus the value here. It's the same thing, but with a minus sign. So, okay. And then the actual matrix of f of x is equal to this. Notice this thing. It's actually a 2x2 matrix involving x1 and x2. Well, here it is. Here you can see it. So writing f of x as a matrix is the matrix of the transformation here times the matrix representing the position vector in LPGG geometry, 0, x1, x2, 0. I think this is completely new. I don't know anything about it if it isn't. Well, I have never seen it. I think this is what was missed. Okay.
At this point, I think it probably would be appropriate for me if I break at this point. I encourage you to continue to discuss this. I certainly look forward to seeing a copy of this paper when you have it in a form that you can distribute.
Yeah, I'd like to make it a little bit better, but let me just go through this last section. It's very short now. I'm just introducing new notation. Okay, what is wrong with this? Is this right? Oh, okay. So I'm really only up to here. I'm trying to modify. This is just from the other paper. I lifted from the other paper, pasted it in. So you'll recognize exactly, that's exactly what Hayes pasted, showed us from the other paper. And I've changed it a little bit, but I have to work on it more. So I'm really finished up to here. That's where I'm at. What I did just before I logged in to Zoom today to talk to you. So I've actually completed a very shortened discussion of what I have to say, but I need to really work on this a little more. But I think the ideas are much clearer here now, and you can understand exactly where it's going. So.
Okay, great. So I have to leave at the moment, but just in a bit of a rush, so sorry about that. But let's meet again in 2 weeks, and we'll see. Hopefully you'll have a draft to us before then, and
I'll send you a copy of this in the next couple of days. Probably I can finish what I want to do right now, and I hope that. Great. I hope that Jesus will send copies of the paper with Sobczyk and the other person, as well as those beautiful figures that he has. I'd like to start seeing if I can apply some of the ideas which I've worked out here to those graphs. I think it can be applied to any graph. And that's what I think it would be. We could write some beautiful papers. I see all kinds of applications of this stuff. I've been very excited about it.
Okay, I've got to run. So see you in 2 weeks.
Okay.
Okay.
See you, Professor Pesh. Okay. In my presentation, there is one more aspect that is needed for working in the way of multigraph. That is to convert this complete graph in a tree graph. Then, if I get, I have the procedure for that, but not implemented yet. But I can show to you the idea of this. Here I have one draft that I made.
Okay, I guess Bill's left, but I guess we can still talk a little bit here. Okay, I see it.
Okay, here we have now. This is okay. Here is the idea. From one of the complete graph that maybe I can put here for reference only, but we have 1, 2, 3, 4. Maybe those was in this way, and then we have this, and we have the other. And then we have here. Oh, sorry for. It is not too much clear, but
okay,
I hope.
I see it perfectly.
Okay. Then from this, I get this.
Oh, okay.
And this is too much important because we can use here the graph of graph language, because
okay. So you're changing a graph into a categorical type picture that you have on the left there, I guess.
Yes, this is the idea.
So then, that's interesting. That's very interesting. in comparison to what I'm trying to do is make an analytic way of studying these graphs in general. So it'd be interesting if we can combine these ideas together, I think.
Yeah. And here, for example, we have one first order graph that are grafting in the tree. Here we have, as I am going to use a different color here, because this is a zero order graph. Then we have here only one node, but here we have two nodes in red color. And after we can get three nodes. I am using the Opera language here.
Okay.
Then this is too much interesting because now we have a 4 order node.
But by the way, could you tell me what graphics program you're using there? I'd like to get that myself. What is it? It's beautiful.
Yeah. And then we only need to make grafting of different orders of graph, and then we can go, but we need to get the exact sequence here to G1 and here to G2, excuse me, G2, and here, and so G3.
So what is G0, G1? That's, what does that mean again, the notation? G0, G1?
This is G0, G1.
Oh, okay, okay.
G2.
I see. Oh, you're constructing it. Oh, okay, using that upside down tree. That's extremely interesting. Great.
Yes.
Okay, okay.
Here is G4.
Beautiful.
And then after I need more space here, but maybe with this color. But here is the reflection of this graph, and this is this reflection is the duality graph, dual graph, and then at the end we need only to connect one of these with this, with this, with this, and so.
Huh.
And then we get the complete graph with this category and the opposite category.
Beautiful.
This is the idea. Not easy in the paper, but I can add this maybe in one draft in a PDF.
Okay, very interesting. Very interesting. But Jesus, can you tell me what graphics program you're using there? I'd like to get that myself to make these beautiful pictures you've just made. What graphic program?
It was Mathematica.
But this graph that you're showing me is in Mathematica, or this software?
Yes, Mathematica software, and I'm just using the the functions built in Mathematica.
So what version of Mathematica is that?
This is Wolfram Mathematica version 13.
15, right?
13, yes. Mhm.
So I have an earlier version. I don't think it has that capability. That's beautiful. It's, I guess that's $1,000 program, right? Costs $1,000 or whatever it is.
Yes, it is expensive, but but certainly this work nicely.
Oh, beautiful.
But
Okay.
In fact, for the way of including this is good in Mathematica for exploration of these properties that we are using. But for including in a paper, we can use directly in LaTeX. I have here one example. Oh, okay. We can include in LaTeX without problem. I want to show to you how in LaTeX it can be built. For example, this. And we can build more complex graphics, of course, in LaTeX without problem.
Okay, so this is all part of category theory, the language you're using then, right? Or essentially.
Yes, actually, this is the language that we are using. Mm-hmm.
Huh.
And this is using category theory language that we can get this. I don't remember some. Okay, I have not enough time for make more slides, but then we can include without problems in the document, not like image, but like objects in the paper. Then,
okay. I think I get the idea, and it's extremely interesting. And please send me a copy of that beautiful paper with you and Zbyszek and the other person, and also whatever graphs that you can send me in PDF format, so I can study them and try to work out some of the simplest ones using what I think an analytical approach to the same ideas, which is, I think, is what we're talking about. That was extremely interesting.
Okay, I am going to send to you this other paper that is the network of network. This was published with Professor Osier in 2004, I remember. And this is an extension of this idea of graph to multigraph. Then here we work in a more general approach, and then we get many interesting relations, graphical relations for graphs. Then I am going to send to you this. Yes. But here the idea of graph is extended, for example, like this. we have two index now for describe the degree of one graph, and then we can extend to more index dot, and then we can build too much general approach for those. Then I think it could be interesting to try to extend your ideas to this kind of formulation.
Oh, I think it's very possible. Very beautiful. By the way, you know, I'm coming to Mexico December 6th to July 13th.
Okay. Okay.
Very soon.
Okay. Maybe we can meet in some time. I love it.
I hope so. I hope so. But I have many things I have to do in Cholula, but I hope we can get together sometime during that period of time.
Okay.
It'd be very interesting to talk in person. It's pretty hard to get out to FESC, of course, but well, we can maybe work something out.
Okay. Okay. Then maybe we are going to have a vacation at that time since December 12th.
Yeah, maybe we can meet on the top of Popocatépetl at the restaurant there or something.
Okay. Okay, then maybe we can find there.
Okay. Okay. Well, I guess we should stop then.
I'm going to stop here.
Is this being recorded, by the way, or not?
Yes, I think it is recorded by.
Okay, very interesting.
Okay. Mm-hmm.
Okay, so
okay, see you.
I've enjoyed it very much. A beautiful session. Take care.
Thank you.
By the way, congratulations on Mexico and Poland, a tie. The soccer. Congratulations, a tie.
Okay. But they played yet or not?
Oh yes, it was a tie between Mexico and Poland yesterday.
Yesterday was?
Oh, Ochoa. Ochoa is now a saint of Mexico.
Oh, okay, okay.
Okay. Take care.
Bye. Bye.